Good evening and happy Wednesday. We finished function definitions and domain and range last time, right? We had our first quiz due today. We're going to be moving on. We're going to be looking at average rate of change. We're going to be looking at the behavior of graphs and how we can combine functions, so function algebra, right? Adding functions, multiplying functions, dividing functions, and composition. So let's just jump right into it. Looking at behavior functions. We also look at average rate of change. Right. Average rate of change of some function, let's call it f of x, over some interval, let's call it the closed interval a to b. It's delta f sub average. Right, it's f of b minus f of a over b minus a. You may also see it written as delta y over delta x, change in y over change in x. If we look at a graph, call this graph f of x. Right? Here's our point a f of a. Here's our point b f of b. Let's take a look at the line that goes through those 2 points. This is a secant line. How do you find the slope of a line? Hmm? Well, that's the equation of a line, right? That's the slope-intercept form of a line, where m is the slope. So how would you actually calculate m? It's rise over run, which is change in y over change in x. So isn't the slope of this secant line? Stop moving. F of b minus f of a over b minus a. Which is precisely the average rate of change. So you can also say that the average rate of change of a function over some interval is just the slope of the secant line that passes through the 2 points, the 2 endpoints. In calculus 1, we will expand on this idea. But back to the problem at hand, we want the average rate of change of 7x plus 12 over the interval 2 to 8. F of 8 minus f of 2 over 8 minus 2.
Next to the delta symbol, is that an F?
Let me turn up my volume. Can you repeat that?
Next to the delta symbol, is that an F where it says after average?
Right here, it's F. Yeah, it's F subscript AVG.
Okay.
But notice what happens. I write it in this form. You can drop out the 12s. Ends up being 56. I don't know why I wrote 2 times 8. And 7 times 2 there, which would make that 14. Right, we get 56 minus 14. Over 6, which is 7. The average rate of change of our function f is 7. Units for the average rate of change. Units of y per units of x. Right, in this case, we weren't given units, so we don't need to include them in the problem. And the 12s do cancel out because it winds up being 12 minus 12, which is 0. Okay. F of x, so it's a bit bigger. F of x is 3 minus 5x over 9. We're on the interval -5 to 0. Oops. F of 0 minus f of -5 over 0 minus -5. F of 0 is 3/9 minus f of -5 will wind up with 3/9 minus looks like -25 over 9. And then all over 5. And 25/9 times 1/5, right? Remember, multiply the numerator by the reciprocal of the denominator. We get average rate of change of 5/9. Oh, I'm sorry, that should be -25. Right? Because of this negative here, there's 3 negatives. When we look at symmetry, there are several types of symmetry for a graph. 3 in particular that we're going to focus on. Symmetry with respect to the y-axis, with respect to the x, and with respect to the origin. So a relation symmetric with respect to the y-axis if both x and negative x result in the same y. Symmetric with respect to the x if both y and negative y result in the same x. And symmetric with respect to the origin if replacing x with negative x and y with negative y results in the same relation. So for the next several problems, we are going to determine what type of symmetry each relation has. Right? Y equals 4x. Let's test the y-axis. Right, so what we're going to do is replace x with negative x. Wind up with y equals negative 4x, right? Now what we do is we ask ourselves, is that the same relation? Are those relations equivalent? Okay, well, they're clearly not, right? The x be 1, you get 4, and then you'll get negative 4. They are not the same. So we do not have y-axis symmetry. X-axis. Replace y with negative y. Determine if you get the same relation. Y equals 4x versus negative y equals 4x. They are not the same, right? They're not equivalent. So we do not have symmetry with respect to the x-axis. Finally, with respect to the origin, we will replace both y with negative y, and x with negative x. When we simplify, we get negative y is equal to negative 4x. Is that the same thing as y equals 4x? It is. That means that our graph is symmetric about the origin. I just here too. Back. Now we're going to look at the relation x squared plus y squared equals 8. Let's see if you're correct. So to test the y-axis, replace x with negative x. So negative x quantity squared. That's just x squared, right? So we get x squared plus y squared equals 8. Well, that's the same, right? Testing about the x-axis, replace y with negative y. That gives us the same. And then about the origin, shouldn't be much work required for this one. We're replacing both x and y with negative x and negative y. We see we get the same. So this has all three types of symmetries. which if you know what type of relation this is, you know you should have gotten this result. Right? X squared plus y squared equals 8 is a circle of radius root 8 centered at the origin. So what I'm going to do is show you a nice feature. Why is Windows Firewall being weird today? So if you're using the TI Inspire, when you first turn it on, you should come to this screen here. Right? You have Scratchpad. You also have documents. So this calculator can actually save a calculator screen. It's called a document. Useful if you're doing like a test and you want to save your calculations. I typically just use the Scratchpad. So I'm going to go to Graph, right? Now this middle icon here, right? You should see you have a big square, you have the 4 arrows, and then in the middle, you have a smaller square. That actually serves as a mouse pad. So if you scroll your finger through there, it'll actually scroll this arrow right on the calculator. So we can just scroll to graph, and then if you click it, so this is going to allow us to do standard graphing stuff, right? Y equals a function of X. But what we can also do is if we hit menu, graph entry, we can also graph relations. Not sure about the 83 or the 84 if they can do this. I haven't used an 83 or an 84 in decades. Right now we can just type in the equation we want, right? So x squared plus y squared equals 8. Hit enter. And there's your relation. And then this we can just move. We can also just get rid of it. All right, so this would be useful if you want to double check your work. Now let's take a look at the relation x times y squared is equal to 1. And again, let's start. Let's look at the y-axis. Remember, for the y-axis, we replace x with negative x. Which gives us negative xy squared is equal to 1, or we can rewrite that as xy squared equals negative 1, right? No, that's not the same. Now check about the x-axis. Replace y with negative y. Negative y quantity squared is just y squared, right? We get x y squared equals 1. That checks out. We have symmetry about the x-axis. Check about the origin. Now we replace both variables, right? We'll again get xy squared is equal to negative 1, so we do not have symmetry about the origin. This is only symmetric about the x-axis. If you have symmetry about both x and y, then yes, it will be symmetric about the origin automatically. If it's not symmetric about x and y, that does not necessarily mean you have symmetry about the origin, though. It is possible to have no symmetry. Correct. If it's symmetric about one of the two axes, but not the other, then you cannot have symmetry about the origin. Right. It was what? Xy squared equals 1, right? Look what happens. So this is an error. Does anyone have an idea why we're getting an error for this? And it wants to create a new slider. So what do we think? Well, if it thought we were multiplying, we wouldn't be having an issue, right? Now, the calculator does know PEMDAS. It does have to do with multiplication. And so you were really close. It's reading this as a single variable. So it does not recognize this as an implied multiplication. It reads it as a single string, not a product of strings. So what we have to do is actually physically type in x times y, right? We can't just write xy. So what it was doing is it was reading that as a single variable xy squared, right? So like z squared equals 1. Instead of x times y squared equal to 1. Now look what happens if I hit enter. There you go. Okay. And the reason for that is, if I just come over to calculate real quick, control 0, and let's say I want to store some value and I'm going to call it, I don't know, say I'm going to store it like a temperature or something. I can represent temperature as the variable temp. Right, I can go let temp be 72. Right. What it'll do now is read temp as the string. So if I just type in temp, you'll notice it's going to turn bold. And if I enter, it's going to recall that value that I just stored, 72. So whenever you're dealing with multiple variables and you want to do multiplication, you have to physically type it in. You have to physically type in the multiplication. All right, that is also true if you get into any kind of coding. Which for this course, obviously, we're not going to, but for future courses, especially in math, you may have to code. Right, so you can store variables as strings, right? So again, temp is a single string. If you want t times e times m times p, you'd have to write out those multiplications. that also means theoretically there's an infinite number of variables you can store. So let's look at the relation x equals y squared plus 1. Let's check the y-axis. Replace x. All right, that doesn't work out. Check the x-axis, we replace y. That does check out. And then the origin. All right, we already know we can't have it. So all we have is symmetry about the x-axis, right? And you're correct in this case is that exponents are the key, but that's because we're dealing with very simple relations. We'll eventually be looking at relations that are not as simple. Right, so we'll be looking at, like I said, things like exponential functions, logarithmic functions, trig functions. Right, so they're not as easy to see. So that's why it's key right now to actually understand what we mean by these three types of symmetry. So being able to do all this algebraically. Let's take a look at the relation y equals x cubed. Check the y-axis. Negative x quantity cubed. So we get y equals negative x cubed. That's not the same. Check the x-axis, replace the y. Right, we get negative y is equal to x cubed, so that's not the same. Now check the origin. Negative y equals negative x cubed. They are the same. So we only have symmetry about the origin. Now have y equals square root of x. If you place x with negative x, you get y is the square root of negative x. They are not the same relation. Keep in mind, square root of negative x is defined. If we look at f of x equals square root of x, what's the domain? Not all real numbers. Just greater than 0? Right? Non-negative real numbers. So what this symbol here means, those are the positive reals. If g of x is square root of negative x, what's the domain? Just less than? Still can be 0, right? Square root of negative 0 is still 0. Right? Or the non-positive reals. Still a defined function. It's just that the domain changes, right? X-axis. We get negative y equals the square root of x. Well, that's clearly not the same. So what about the origin? Are they the same? Negative y equals square root of negative x. Is that the same as y equals square root of x? If I divide by negative 1, we get y equals negative root negative x. Why would it? Right? Normally two negatives, negative times negative is positive, right? What you're trying to do is this. And then say the square root of negative 1 is negative 1, which it is not. Right? Remember, when you factor something out of a square root, you have to factor out the square root, right? So, for instance, square root of 4x is 2 root x, right? Not 4 root x, because you're factoring out a square root of 4. Those are not the same. So this does not have any of the 3 symmetries. This does not mean, however, that it does not have any symmetry. Right. Fact of the matter is, y equals square root of x doesn't have any symmetry. However, I can easily come up with a relation that doesn't have any of these 3 symmetries, but still has symmetry. It would be just as it was in the instructions. It would say, determine whether the graph is symmetric with respect to the y-axis, x-axis, origin, or none. Is this relation symmetric about the y-axis? Is it symmetric about the x-axis? What about the origin? But it does have symmetry. It is symmetric about that orange line. What line test? What line test are you talking about? The vertical line? That just determines whether it's a function or not. Right, this is a function, but it doesn't tell us anything about symmetry. Right, so you got to be careful when you're answering these questions, right? In this case, you'd be safe, right? For number 8, you'd be safe if you said it has no symmetry, because it actually doesn't. But if I gave you that relation, saying it doesn't have any symmetry is not correct, because it does. It just doesn't have any of the 3 types of symmetry that we considered. But in fact, a circle, let me just plot it, because I don't feel like trying to draw a circle. Right, this circle, not symmetric about the y-axis, not symmetric about the x, and not symmetric about the origin. But it has an infinite number of symmetries. Draw any straight line through this circle, and it's going to be symmetric about it. Right? But those symmetries are a bit tougher to test for, which is why we ignore it. Right, one more thing I want to discuss about symmetries. Fairly certain this concept was introduced in this lecture video. the idea of even and odd functions. Consider All right, so consider a function from the reals into the reals. Right, we call f even if f of negative x equals f of x. Even functions have y-axis symmetry. We say that f is odd if f of negative x equals negative f of x. Odd functions are symmetric about the origin. Right? So this idea of even and odd functions is going to be extremely important when we study trigonometry. Correct. Right. So unlike integers, which have to be either even or odd, functions can be neither. Right. Easy function, x squared plus 1 is neither even nor odd. Wait, I'm sorry. No, x squared plus 1 is even. X squared plus x is neither even nor odd. But other properties are similar. Right. So if you take an even function and multiply it by an even function, it's even. Take an even function by an odd function, it's even. And if you take odd by odd, it's odd. Wait, is that? Let me double check that. Odd function. No, I'm sorry, odd times odd is also even. Okay, so I got that wrong. If you multiply an even function by an even function, it's even. An odd function by an odd function is even. And an even by an odd is odd. And we're going to be studying how to multiply functions after the break. But that'll be important with trigonometry. A function cannot be both even and odd. That's not possible. Right? If you had a function that was both even and odd, that would mean to be symmetrical about both the x and the y. But if it's symmetrical about the x-axis, it's not a function because it would fail the vertical line test. Right, so that would be what we call a contradiction. So increasing, decreasing. So again, we're going to consider functions from the reals to the reals. Right, so we say a function is increasing over an open interval AB. If f of x1 is less than f of x2 for every x1, x2 in the interval, such that x1 is less than x2. Right? In other words, as you move left to right in the interval, your values of the function are getting larger. Right? So this symbol means in or element of. Well, and guess what decreasing means? Right? Means the values of your function is getting smaller, right? So f of x1 is greater than f of x2 for every x1 and x2 in your interval, such that x1 is less than x2. Right? Now, I can't just give you a function without its graph and ask you to determine whether it's, find intervals in which it's increasing and decreasing. We can't do that yet. We have to use the graph. Once you take calculus 1, you will be able to. Also in the lecture video was introduced the concepts of absolute or global extrema and relative or local extrema. Right, so mins and maxes. So we're going to look at this graph and we're going to estimate intervals on which it's increasing and decreasing, right? The best we can do is get an estimate. We can never say for certain just from a graph that these are the exact intervals, because graphs are not necessarily drawn to scale. So let's determine where it's increasing. Looks like it's increasing over this interval, right? So let's say looks to be about -3/2 to 2. Right? Is that exactly -3/2? Don't know. That looks close enough. Right? Now, where is it decreasing? Well, it's decreasing to the left of -3/2, right? Where are you getting 2.5 to 3.5 from? It doesn't stop at 3.5, does it? It'd be 2 to infinity as well. Right? So, yes, I agree. It starts decreasing at 2 again, right? But it's going to continue to decrease forever, right? So 2 to infinity. But it's also decreasing negative infinity to negative 3/2, right? So there are actually 2 intervals on which we have decreasing. By the way, it is possible for a graph to be neither increasing nor decreasing on an interval, right? So this piece here is constant. It's neither increasing nor decreasing. Right? So keep that in mind. A function doesn't have to always increase or decrease over an interval. It could also be constant. Okay, you going to sync for me? Yes, we do. Oh, I'm using the wrong bloody mouse. Because there are arrows here. Right, there's an arrow here, which means it's going to continue in that way forever. And the arrow up here means it continues in that manner forever. If those arrows weren't there, then no, we couldn't say that. Right, but then what we do is we just consider those points closed. And so our domain wouldn't be all real numbers. Let's look here. Where does it look like it's increasing? Negative infinity to negative 2.5. I agree. Is there anywhere else? And I agree. Yes, 1 to infinity. All right, so this line looks to be about negative 5/2. That line looks like it's at 1, right? So it's definitely increasing to the left of negative 5/2 and to the right of 1. Then what about decreasing? -5 to 1, I agree. Depends on the fraction. As a general rule of thumb, always leave it as a fraction. And again, in mathematics, it is customary not to use mixed numbers, to use improper fractions. Right? Something like -5 being written as -2.5 is fine, right? Because that is exact. But 1/3. 1/3 is 0.3 repeating forever as a decimal. Right, so you can't just write it as like 0.33. That would not be exact. So like I said, as a general thumb, just leave it as an improper fraction. And there's going to be a lot of things you notice that you learned in high school math that was actually a lie, right? So you were told, for instance, that was unacceptable, right? You were told you have to write it this way because you're never allowed to have radicals in the denominator. Yeah, that's a lie. That's typically how we would leave it written. Same thing with improper fractions, right? I believe that you were taught that you shouldn't leave it improper. Right? You're taught to write it that way. Yeah, that's a lie. This is actually how we want it. So that is a bit more difficult to answer. It depends on how complicated the simplification is. Something like this, yes, has to be simplified. But if you're dealing with a really complicated looking expression, you don't have to fully simplify it unless the problem specifies to. Right, so something like square root of 96, that would be acceptable, even though it's not simplified. Right, 96 is divisible by 4. So it's 4 times what? It'd be 4 times 24, I believe. Yeah, because 4 times 25 is 100. So this would be 4 times 24. Oh, but 24 is also divisible by 4. Right, that's what? 4 times 6, right? So this is actually 16 times 6. So you could write this as 4 root 6, fully simplified. But I'd be okay with either one. But something like 4/8, which is obviously 1/2, that will have to be simplified. So the obvious simplifications you do have to make. Right, but again, it is custom. Never mix numbers in mathematics. Always improper fractions. Always leave it as an improper. And you don't have to worry about rationalizing the denominator. 3 over root 5 is actually preferred to 3 root 5 over 5, right? Because 3 over root 5 actually looks simpler. It's actually simplified. All right, what about this function? What does it look like we're increasing? The unit tests will typically be between 5 and 10 questions. In terms of study guides, I usually don't post study guides for tests. There might be a study session for the final exam, so I might post an old final exam that we go over. Right, but obviously final exam is still a little ways off, so you don't have to worry about that. A good rule of thumb, if you can do well on the quizzes, you're probably going to be fine on the test. And so if you can do well on the homeworks and the quizzes, you're probably going to be fine for the test. So use those as your study guides. And don't forget, I will be posting the quiz solutions once I post the grades. So increasing, we have negative infinity to 1. Is there anywhere else it's increasing? What do you think the start point is? Would be 3 to 4, open. Right. Right, never hits 3, but that's what the open means. Right, because what's happening, right, is this goes down forever. It's going to get closer and closer and closer to that line 3 without ever touching it. And that's what this means, right? Some arbitrary number that's slightly greater than 3. So would you agree that it is increasing here? I don't know if you can see my do this. What I just drew in red, that's increasing. All right, you agree with that? That is increasing. Right, before I can answer that, you have to understand that this is increasing, right? This bit here, you do agree, is increasing. Right? So where does it stop? Clearly stops at 4 here, right? So what you do is you look and go, okay, so how's it behaving to the left of 4, right? Because we agree that at this point to the left of that line, it's increasing. Well, the graph is going to keep going down, down, down. It's going to approach, if you look, it's approaching that orange, isn't it? It's going to get closer and closer and closer to that line, but never touch it. And so that's how we get the starting point of 3. Another way you can look at it is if you actually look at the graph, isn't there a jump at 3? Right? You have 2 different curves, and it's split by 3. You see that? Right? So 3 acts as like a dividing line between the 2 graphs, right? So that is how we got this 3 as a starting point. You see that? Does that make sense? I'm going to take that to mean yes. So then where is it decreasing? Where else? So 1 to 3 union with 4 to infinity. And again, decreasing to the right of 1. Okay. So I think we're going to then stop there and take our 10-minute break. So we'll come back at 7:50. Okay. Continuing on, we are now going to look at combining functions. There are 5 operations on function. Well, I guess 6 operations on functions. We have addition, we have subtraction, multiplication, division. Then we have composition and inverse. However, inverse functions we don't look at until tomorrow. So consider functions f and g that have domains d sub f and d sub g respectively. So f plus g of x is f of x plus g of x. This is also a function. And its domain is the intersection of the domains. F minus g of x is defined as f of x minus g of x. It is also a function. And it has domain as the intersection of the domains. F times g of x is defined as f of x times g of x. It is also a function. Its domain is also the intersection of the domains. Excuse me. F over g of x is defined as f of x divided by g of x. This is also a function. It has domain. Intersection of the domains minus any value in the domain of G that makes G of X 0. All right, so that forward slash is set minus. And just so we don't have to keep scrolling back and forth, I repasted the problem. F of x is x plus 1 over x squared minus 4. G of x is 2 over x. Let's first find their domains. So what is the domain of F? Anything but 2? So you're saying this? Anything but positive or negative 2, right? What is the domain of G? It's a bad looking infinity. There we go. Right? There's our domains. First, we need F plus G of X. All right. That is F of X plus G of X. And remember what the rule is for adding two fractions. We need a common denominator. So first term of our numerator is going to be x squared plus x. Second term will be 2x squared minus 8. Right? Yeah, let me do that. Let me actually distribute that x through and just write that as x cubed minus 4x. So there's an expression for f plus g. Now we need its domain. So remember, the domain is the intersection of the domains. Intersection of two sets is the set of everything that they have in common. So if you look at the two domains, what values do those two domains have in common? So what values do they share? Right? Everything except for -2, +2, and 0. So there's the domain. All right, f minus g. So in this case, if you plug in a -2, you are going to get 0 in the denominator. Right? But it doesn't matter even if you don't, because -2 makes f of x undefined. An undefined value plus something is still undefined. Which is why we exclude it. All right. So f minus g is going to be the same thing, except it's now minus instead of plus. right? So if we simplify this, we now get negative x squared plus x plus 8, right, over x cubed minus 4x. Its domain is the same as plus, right? It's the intersection of the domains. Right? F times G is f of x times g of x. Right? Multiplication, you just go straight across. So that would be an expression for f times g. The domain of f times g is also the intersection of the two domains, right? So it's going to be the same. Well, it's not a coincidence, is it? Because how do we find the least common denominator? By multiplying the denominators together. And that's how we take the product, right? We just multiply straight across. It just so happens that f plus g, f minus g didn't simplify. Right? There wasn't a common factor in both numerator and denominator to cancel out. Now we want f over g. Well, that is f of x over g of x. Remember, when you divide fractions, or when you simplify a complex fraction, you multiply the numerator by the reciprocal of the denominator. Its domain is the domain of f intersected with the domain of g. Then we have to take out any element in the domain of g that makes g of x equal to 0. Well, we already know what the intersection is. Now we have to take out all elements in the domain of G that make G of X equal to 0. So a little bit of side work. G of X is 2 over X. 2 over X equals 0 means what? So values of X that make 2 over X equal to 0. Right? 2 over X equals 0 would mean that 2 is equal to 0, which is a contradiction. That means that this set here, this part here, is the empty set. So there's nothing to remove. So the domain is the same. No, we check the original function. Right? The original function was the 2 over X. So we just say, okay, when does 2 over X equal 0? We have to remove those elements from the intersection. In this case, there was nothing, right? So there's nothing to remove. I believe I do have a case where we are going to have to remove stuff. I do. Right. Now, I want you to notice something. If this expression was all that you were given, what happens if you plug in 0? And so what do you get if you plug in 0 to what I have boxed? Is it? It's 0 over -8, isn't it? That's 0. So if you just looked at what's boxed, you would come to the conclusion that 0 is in the domain. but yet it's not in our domain. You cannot just look at the end result and get your domain from that. You have to consider the domains of the two functions, right? The reason that 0 is not in this domain is because you would then have a value divided by something that is undefined, which is undefined. Right? You can't take something that doesn't exist and then divide a number by it. Right? That doesn't make sense. So same thing we just did, just two different functions now. First things first. Let's find the domains of these functions. What is the domain of f? Hmm? So we have to have 1 minus x greater than or equal to 0, right? Means x is what? X is greater than 1? Wouldn't that mean x has to be less than or equal to 1? domain of G. Negative infinity to negative 2 closed union with closed at 2 to infinity. All right, you have to solve that inequality, x squared minus 4 greater than or equal to 0. Which is actually very simple to do. Means x squared has to be greater than or equal to 4. Which means the absolute value of x is greater than or equal to 2. That interpretation is that all right, look at f plus g of x. Remember, that is f of x plus g of x, right? Can we simplify that expression? Huh? So can that expression be simplified? Uh-oh. That's not what I wanted. You just zoomed in too much. Oh, I think that's where I had you. Right? It cannot be simplified. Right? Remember, you cannot combine the sum of square roots. Now we take a look at its domain. Right? So remember, the domain is the intersection of the domains. So what do the two domains have in common? Is -2 included? Right? That is the intersection. That's all that the two domains have in common. F minus G. All right, it's f of x minus g of x. Once again, that cannot be simplified. And the domain's the same. F times g, f of x times g of x. Can that be simplified? Right? In other words, can we combine the product of square roots? So is the square root of a times the square root of b the same as the square root of a times b? You can. Square root does distribute across multiplication. So that would be our expression. And again, its domain is the same. Now, what about f over g, right? So that's going to be f of x over g of x. Right? The only simplification we can make is to put it all under one square root. Right? Otherwise, there's no other simplifications. Nothing's going to cancel. Right now we need the domain of f over g. Right? Well, we know that that's going to be the intersection of the domains minus whenever g of x is equal to 0. That would mean that x squared minus 4 is 0. So x squared is 4, meaning the absolute value of x is 2, which is -2 or +2. Right? So we take out -2, +2. So here's how set minus works. Look at the first set. From this set, we take out every element that's in the second set, right? So you look, okay, -2, is that in the first set? Yes, so you remove it. +2, is that in the first set? And it's already said no, right? So you don't have to worry about removing it because it's not there. So it's no longer closed at -2, it's open at -2. So that would be our domain. Okay. So function composition. I'm going to do it this way now. And so this is technically composition of functions. So the domain of the composition is the domain of F. No, that's not right. Yeah, ignore that. I don't want to go into functional analysis. I'm just going to go back to what I was going to do. Make these just reals. So you have two functions, f and g. Their composition, f composite with g, is defined as f of g of x. This is a function. Its domain is the set of all values x in the domain of g such that g of x is in the domain of f. Okay. Might make more sense when we go ahead and actually do it. So as before, let's start by finding the domain of the two functions. So the domain of f be 6 to infinity. Domain of G is all real numbers, right? First, we want F composite with G. That would be F of G of X. Well, that's F of X squared plus 5X, right? Because that's what G of X is equal to. Everywhere we see an X in the definition for F, we're going to replace it with X squared plus 5X. So that would be our expression for F composite with G. So now we need its domain. So remember, it's going to be the set of all values within the domain of G such that G of X is in the domain of F. But here's what we're going to do. G of X, X squared plus 5X. We want values of X that make that in the domain of F. In other words, we want values of X that would make this expression greater than or equal to 6, right? Because that is the domain of F. So that means we have to have X squared plus 5X minus 6 greater than or equal to 0. Right? Right? We looked at solving inequalities already. We need breakpoints. So that can be factored to X minus 1 times X plus 6. That equals 0. So our breakpoints would be X equals negative 6. X equals 1. We need to test the signs. If we take any value from minus infinity to minus 6, plug it back in. This will be plus. That one will give you a negative. That one will give you a plus. So that gives us a solution. of negative infinity to negative 6 and union with 1 to infinity. Well, since the domain of G is all real numbers, that would be our domain of f of G. Right? So negative 5, if you plug into G, would be what? 25 minus 25, which is 0, isn't it? 0 is not in the domain of F. And again, yeah, that would give you a negative in the square root as well. But you don't want to really look at that much like before. You want to think in terms of just the domains, not of the expression we just found. We also wanted G composite with F. This is G of f of x. Right? G of the square root. What was f? X square root of x minus x. Right? That means that everywhere we see an x in the definition of G, we're replacing it with a square root of x minus 6. Square root of x minus 6, all squared, is what? Just be x minus 6. Right? There would be our expression for G composite with F. Now for its domain. This time we're looking for the values in the domain of F that make f of x in the domain of G. Written another way, We want values of x that are greater than or equal to 6 that would make the square root of x minus 6 a real number. Well, isn't that just every single value then? Lowest what can be is 1. But yes, the lowest the square root can be is 0, right? Which is a real number, right? So everything from 6 to infinity, take the square root of that minus 6, you're going to get a real number. So that's why the domain is just the domain of f. Same thing, different functions. Domain of f. Four minus x plus 5. If you're trying to give me the composite, I'm not looking for that just yet. Right now, I'm just looking for what the domain of f is. Right, just like before, we want to find the domain of the two original functions. Yep, it's all real numbers. The x squared plus 5 will never be negative. What about the domain of g? Everything less than 2? It would be the closed interval -2 to 2, right? Of course, the endpoints are included because you can take the square root of 0. F composite with g? f of g of x, so we want f of square root of 4 minus x squared. Replace x with root 4 minus x squared in f. We'll get the square root of 4 minus x squared plus 5. Which is the square root of 9 minus x squared. Domain would be all x in the closed interval -2 to 2, such that the square root of 4 minus x squared is a real number. So what values from -2 to 2 make the square root of 4 minus x squared a real number? It would be all of them, right? So that's our domain. Now we want G composite with F. That is G of f of x. That'd be G of the square root x squared plus 5 All right, we're replacing in G x with x squared plus 5, square root of x squared plus 5 rather. And you should find that gives us the square root of negative quantity x squared plus 1. So where did you get confused? So what's 4 minus 5? And then minus x squared, right? All I did was factor out a -1. Again, that's pure preference. The domain is a set of real numbers such that the square root of x squared plus 5 is between -2 and +2. Let's do some math. So here's the inequality we have. Square both sides, or square everything. Four is less than or equal to x squared plus 5, less than or equal to 4. This means that x squared plus 5 would have to equal 4. But wouldn't that mean that x squared would have to be -1? Which in the real plane, which is what we're working with, real numbers, is a contradiction. That means there is no real number that makes this inequality true. This domain is empty. Which means this isn't even a defined function. It is not a function. Well, let me rephrase that. It is a complex function. Right, so it's a function from complex numbers to complex numbers. Those types of functions we do not study. That is well beyond the scope of precalculus. In fact, you don't even study those types of functions until a senior level math course called complex analysis. Right, so you're only going to really do that if you're a math major. Okay. Last type of problem we're going to look at is given a function, we want to break it down into two functions so we can write it as a composition, f of g. Now, this is very, very, very important in calculus. Right? Theoretically, right? So theoretically here, there would be an infinite number of ways to do this. Right? I'm going to look at the simplest way. So what I do is I look and I go, okay, my g of x is the inner function, right? So I look here and I go, okay, what is the inner function? Well, it looks to me like it's 5x minus 3. What is g of x being raised to? It's being raised to the fourth power. So my f of x would be x to the fourth. So there are my two functions, f and g. See that? It's not the only solution, right? Those are not the only two functions. But this is how we would do it in calculus. So this is just the way that I do it. All right, let's look here. Square root of 1 minus x squared. So what would you make the inner function g of x? And then what would your outer function f of x be? All right, just root x. So there's one possibility. Let's do this time to catch up. Right, here's how I do it, right? I want to write as f of g of x, right? G of x is an inner function. So I just look at this here and I go, what is my inner function? Right, in this case, what's under the square root? It's 1 minus x squared, right? So that's what I set my g of x to be. Right? Then f of x is the outer function. So what are we doing to g of x? We're taking the square root. So that's how I get square root of x. Okay, what's going on? Okay, if I go back to full screen, oops. If I go back to full screen, does that fix it? It does. Excellent. Okay, so now what about here? Right. Well, here what I do is I'm going to look at overall, doesn't this seem to be x to the negative 2/3 power? Right? It's 1 over something raised to the 2/3. But what's being raised to the negative 2/3? The x squared minus 5x plus 6. There's my f, there's my g. Right? Again, not the only two functions, but it is the simplest. Any questions? Okay.